average and expected value. Suppose we generate 1 million random variables, xi, all independent, all from a distribution with probability function f of x. For example, they might be Poisson random variables. At the bottom of the page, actually, you'll see our code for generating exactly these random variables and then determining an estimate of the probability that x is equal to 0 or x is equal to 1 by counting how many times in that sequence of 1 million variables that occurs. The fraction of times that occurs is called the frequency. In other words, if we count how many times we observe x equals 0 and divide by n in this case 1 million, we get an estimate of the probability that x equals 0. And since we've generated a very large number of random variables, this frequency, the frequency of 0, the relative frequency of 0, should be close to the actual probability. In other words, f of x, where x is 0. If we were interested in the average of all 1 million x's, one way of counting this would be to put in the numerator 0 times the number of times we obtained 0, plus 1 times the number of times we got x equals 1, plus 2 times the number of times x equals 2, for example, and dividing by the total number of variables, little n. In other words, 0 times the frequency of 0, plus 1 times the frequency of 1, and so on. Expected value. For large values of n, we think the frequency of a value, x, should be close to the probability that the random variable takes that value, the probability x equals little x, or the probability function, little f of x, which is to say that the average of all of the random variables x should be approximately 0 times f of 0, plus 1 times f of 1, plus 2 times f of 2, and so on. This is the sum over all possible x, the values of x, times the probability of this value. The sum over all x, x times f of x. This is the definition of the expected value. If a discrete random variable has a probability function f of x, then the number e of x, the sum over all little x, x times f of x, is called the expected value of the random variable x. We'll denote it by capital E, brackets x, and we'll refer to it either as the expected value, or the mean, or the expectation of the random variable. Remember that it's a number. By the way, when there are infinitely many x's in the sum, we require that the sum x times f of x be absolutely convergent, which is when you take the absolute values, you get a finite sum. Is the expected value really to be expected? Here's an example in which x has a binomial distribution with n equals 5 and p equals 0.5. We've listed the probability function below. The values of x run from 0 up to 5, and the probability of those values, f of x, is listed as well. We've calculated the expected value of x in this case, 0 times the probability of 0, plus 1 times the probability of 1, and so on. And we've obtained the number 2.5. E of x is 2.5. In what sense is 2.5 heads to be expected when we toss a fair coin 5 times? Of course, 2.5 heads can't possibly happen. We might get 3 or 2. Both of those, in fact, have the same probability. We might get 4 or 1, 5 or 0. In the long run, if we have many values of x generated independently of one another, and we average the result, then the average will approach 2.5. It'll be close to 2.5. Expected value is a long-run average. Here's some advice on how to lose money at the racetrack. We go to many horse races and we always bet on the same horse, pictured here, Lame Lazy Liz. The probability that Lame Lazy Liz wins a race is 0.01, 1 out of 100, but the payoff is quite profitable, $90 on a win. Of course, we pay something for a ticket, namely $2. Our winnings, the random variable, can take two possible values, 90 with probability 0.01, or 0 with probability 0.99. So the expected value of x is 0 times its probability 0.99 plus 90 times its probability 0.01, or 0.90. This would be the average long-run gain per ticket if we were to bet on this horse many, many times under identical circumstances. Regrettably, we have to pay $2 per ticket, so on average we lose $1.10 per race. Here's a multiple choice question you should try on your own. If x has a binomial distribution with n equals 4 and p equals 3/4, then the expected value of x is what? Is it 1, or 2, or 3? Is it the sum as x goes from 0 up to 4? 4 choose x, p to the x, 1 minus p to the 4 minus x. Is it none of the above? Or is it all of the above, including e, none of the above? You should pause for a moment and attempt to answer this question on your own. The expected value of x is the sum, in this case as x runs from 0 up to 4, of x times the probability of x, and we've written out that probability function here. 4 choose x, p to the x, 1 minus p to the 4 minus x. We determine the expected value by simply plugging in the value for p equals 3/4, 1 minus p is 1/4, and then numerically evaluating this sum. And it turns out to be 3, so the correct answer is C, which is, in this case, and in many instances, the guess you would probably make for the number closest to the random variable x. If I say the probability of a heads is 3/4, and you toss a coin 4 times, your instinct says that you might expect somewhere around 3 heads. When it comes to expected values, your instinct is very often correct. The significance of expected value. As we've seen, the expected value is the sum of all of the values of x times the probability of these individual values. It's also the fair price that you might pay to play a game whose payoff was x dollars. In this example, you see a probability histogram for the binomial distribution with n equals 6 and p equals 1/3. The possible values of that random variable are 0, 1, 2, 3, 4, 5, 6, but you can barely see 6 in this figure because the probability is so small, it's not graphed. You'll notice that the largest probability, the largest of the rectangles here, is above x equals 2. If we were to cut out this figure, the blue rectangles, and try and balance it somewhere along the x-axis, we would discover that the balance point, or the center of gravity, is at the point x equals 2. In that sense, the expected value of x is also the center of gravity of the distribution, or the histogram for x.